This tutorial will demonstrate hosting a WebSocket server on an ESP32 using the LoBo MicroPython firmware. WebSocket protocol enables real-time two-way data transfer between a server and a client, such as a web browser, in a very efficient and standardized manner. A WebSocket server will broadcast temperature data from a DS18B20 sensor connected to an ESP32. A web page built with React and MobX state tree on a Raspberry Pi will be the client. This is the sixth segment in my MicroPython ESP32 series. My videos are fast-paced, but my website contains complete coded notes for all my tutorials. A link will be placed in the description, along with links to prior videos, which I recommend you watch first if you're just getting started. I've taken the touchpad MP3 circuit from my last video and attached it to the side of a plastic cup. The touch volume slider controls position so it can detect the fluid level. When liquid is poured into the cup, the gauge on the screen reports the level. The ESP32 on the MP3 board is hosting a WebSocket server. The React app running on the tablet is being served by a Raspberry Pi, which is acting as a WebSocket client, and gets instantly updated when the capacitive level sensors on the ESP32 detect change. WebSockets are a great way to provide real-time, full-duplex communication over the internet. React is a powerful and relatively easy solution for interactive web or mobile UIs. There are tons of open-source React components available for download on the web, such as this fluid level sensor, which really expedites coding. For this tutorial, I'll be using the LoBo MicroPython firmware, which has many advantages over the standard MicroPython.org build used in my previous videos. LoBo has support for up to 16 megabytes of PS RAM. This addresses a common problem, which is the limited amount of free memory available when using MicroPython on an ESP32. And many ESP32 boards now come with PS RAM. The LoBo firmware is built as an ESP component. ESP is the expressive official development framework for the ESP32 chip. This means the regular ESP menu config system can be used for the configuration. This supports many ESP32 specific features not found in the standard build. There is SD card support, which greatly increases storage capacity. The LoBo firmware comes with many built-in modules implemented in C, which improves performance and saves memory, such as an FTP server, Telnet server, MQTT client, MDNS, and GSM. Additionally, there's an SSH, curl, a real-time clock with NTP synchronization, threading, a performant TFT display module, and much more. I believe all the code in the LoBo library is either MIT or Apache licensing. Also, Laboris, the creator of the project, has a forum and provides fantastic technical support and is very quick to address issues and implement new features. The LoBo build comes with Jean-Christophe's micro-web server library, which includes WebSockets. I demonstrated this library in my third MicroPython tutorial, which shows how to set up a web server on an ESP32. Like the standard library, LoBo provides pre-built firmware, which makes installation easy. There are several available firmware from bare bones to fully loaded, with features such as SpyRAM, OTA, dual partitions, and additional modules. If your ESP32 board has PSRAM, click MicroPython, LoBo, ESP32, PSRAM, all to download the full-featured build with PSRAM support. If your ESP32 doesn't have the PSRAM, then choose one of the other non-PSRAM versions. The LoBo wiki lists several ESP32 breakout boards that come with PSRAM. In this video, I'm using a Wemos Lowland Pro, which has 4 megabytes of PSRAM. Unfortunately, this board has been discontinued. Once the download completes, open a blank terminal. CD into the downloaded folder. ls shows the firmware zip file. Unzip the file to the current directory. ls shows the uncompressed folder. CD into the new folder. ls again to see the contents. LoBo provides a Flash script that automates the entire process of uploading the firmware to the ESP32. This really makes installation a breeze. You'll need to have the ESP tool installed, which is demonstrated in the first video of this series. dmessage grep tty USB indicates that I have an ESP32 connected to my Raspberry Pi on USB port tty USB 0. /flash.sh tty USB 0 writes the LoBo firmware to the ESP32. In case you're wondering, the video is sped up, but not by much. The Flash script only takes about 30 seconds. Okay, that's all it takes to load the LoBo firmware onto an ESP32. In idle, I have the main.py program used in the last video. Main.py runs automatically when the ESP32 boots. The MicroPython program establishes a connection to my Wi-Fi access point. I'll make a few modifications to implement some of the great features that come with the LoBo firmware. From network, imports are added for MDNS, FTP, and Telnet. An MDNS service is instantiated. After a successful Wi-Fi connection, the MDNS service is started. The hostname is set to MPy. This will allow computers on your network to communicate with ESP32 by a friendly name as opposed to an IP address, which might change. An FTP server is started with the username Pi and password Raspberry. This will afford quick file transfers to and from the ESP32 using any FTP client. It's good practice to pick a better password. A telnet server is started with the same credentials. This allows for REPL access over the network. Before using these new services, the main.py file has to be copied to the ESP32. I'll save the changes and exit out of idle. In a new terminal, our shell is used to connect to the ESP32 via the USB cable. CD into the Documents folder. ls shows the main.py program that I just saved. ls/pyboard/flash shows the contents of the ESP32, which so far only has a boot.py file. Note, the LoBo build expects the files to be in the subdirectory flash as opposed to the root. cp main.py/pyboard/flash copies the main.py file to the ESP32. REPL enters the REPL, import machine, and then machine reset can be used to perform a hard reset of the ESP32. You could also just press the reset button on the board. The main.py file runs automatically on boot and starts the services. My access point is found and the Wi-Fi connection is successful. With FTP and Telnet running, full wireless control of the ESP32 is now possible, and the USB cable can be disconnected, assuming you provide an alternative source of power. From the Raspberry Pi, pinging mpi.local shows the ESP32 MDNS service is working. Instead of the IP address, apps can now reference the ESP32 by name. MDNS service is built into Linux and Mac. It doesn't come with Windows, but can be easily added by installing a free program called Bonjour. And if you have iTunes, it's probably already installed on your computer. In the third video of this series, I built a simple HTML web server on the ESP32 to provide temperature and humidity readings from a DHT22 sensor. In this video, I'll use a one-wire DS18B20 temperature sensor, which is what I used in my server room temperature monitor, which has been running flawlessly 24/7 for over 4 years now. The DS18B20 digital thermometer provides 9-bit to 12-bit Celsius temperature measurements. It communicates over a one-wire bus that only requires one data line, and multiple ones can be daisy-chained together on the same line. Wiring the DS18B20 to the ESP32 is straightforward. The red VDD wire is connected to 3.3 volts on the ESP32. The black wire is connected to ground. The yellow data line is connected to GPIO 23. A 10K pull-up resistor is required between 3.3 volts and the data line. You can use any available GPIO under 34 for the data line. However, there could be a few exceptions because some boards reserve a few of the pins. For example, on the Lowland 32 Pro, pins 2 and 22 don't work. On a breadboard, I have a Wemos Lowland 32 Pro. I've already connected the 3.3 volt pin to a rail on my breadboard. I've also connected a ground pin to the other rail. Here's the DS18B20. This version of the temperature sensor is encapsulated in a waterproof stainless steel tube. I've soldered header pins to the other end of the sensor. The VDD and ground pins are plugged into the corresponding rails on the breadboard. The data line is plugged into an empty terminal strip. A jumper wire connects GPIO 23 to the data line. A 10K ohm resistor pulls the data line up to 3.3 volts. Okay, the hardware is good to go. Now let's take a look at some code. Here's the MicroPython WebSocket server code, which I called WS1. From machine, import one wire, RTC, and timer. From microwebserve, import microwebserve. This is the web server/WebSocket library. Import JSON. A one-wire device is instantiated on GPIO 23. A DS18B20 is instantiated on the one-wire bus. A real-time clock is instantiated. The time is synchronized to ntp.org and the time zone is set. The program can now track the correct time. The ESP32 hardware timer 0 is instantiated. This affords the ability to fire functions at specified intervals. The WebSocket server uses 4 callback methods. cbReceiveText will fire when the WebSocket server receives a text string. The method is passed a reference to the WebSocket server and the message text. For this example, we'll just print the message to the terminal. SendText is also used to send an acknowledgement reply back to the client. cbReceiveBinary is similar to the receivedText callback, but fires when a binary message is received. It's passed a variable data which contains the binary data. Another print statement outputs the data. The callback cbClosed fires when the client disconnects from the WebSocket server. DNet is used to dispose of the hardware timer. The closed status is displayed in the terminal. The callback cbTimer is not part of the WebSocket model. Instead, it will be fired at specified intervals by the ESP32 hardware timer. It's passed a reference to the timer and the WebSocket server. A dict is used to build a JSON message that will be transmitted to the WebSocket client. An entry temp holds the temperature, which is retrieved from the DS18B20 sensor using ds-convert-read. The temperature is also printed to the terminal. An entry internal stores the internal temperature of the ESP32, which can be accessed using the machine method internal temp and referencing item 1. A third entry, time, stores the current time, which is returned by calling rtc.now. WebSocket sendText sends the message text, which is converted to JSON by using the dumps method on the dict. The callback cbAcceptWS is the fourth WebSocket callback and is fired when a client connects to the server. After printing the accept status to the terminal, the WebSocket callbacks created above are assigned. Receive text callback is set to cb receive text. Again, this is the callback that responds to text messages sent from the client. Next, cb receive binary is assigned, and cb closed is assigned. When the client connects, the hardware timer is turned on to periodically poll the temperature sensor. The timer will need a reference to the WebSocket server, so a lambda is used to inject the WebSocket server into the timer callback. Team_init starts the hardware timer. The interval is set to 3 seconds, and the callback is assigned. The microweb server is instantiated. Max WebSockets received length is set to 256. WebSocket threaded is set to true. This uses a new thread for each WebSocket connection. The stack size is set to 4096. Accept WebSocket callback is assigned to cbAcceptWS. This is the callback function above, which fires when a client connects. MWS starts the web server. Threaded is set to false. This results in a blocking call. Aside from the hardware timer and callbacks, which operate independently, the program will wait here until Ctrl+C is pressed. Threaded could be set to true to continue with other operations. Upon Ctrl+C, the web server is stopped. The timer is disposed, and the real-time clock is cleared. That's it for the WebSocket server. The FTP client FileZilla is used to upload the WS1 program from the Pi to the ESP32. Click the Site Manager icon. I already defined a site for the ESP32. The connection is successful. Note that the site took advantage of the mpi local address to connect to the ESP32. Double-click the Flash folder to change directories on the ESP32. Then right-click on the WS1 Pi file and select Upload. OK, the WebSocket server program is now on the ESP32. By the way, that wasn't sped up. The FTP server is very fast compared to our shell. Now close FileZilla and open a blank terminal on the Raspberry Pi. Sudo apt-get install telnet installs a simple telnet client. After installation, type telnet mpi local. The ESP32 prompts for credentials, which were defined in main.py. OK, the ESP32 REPL is now active via telnet. From upysh import star. This is a minimalistic MicroPython shell library to run file commands from the REPL. pwd prints the working directory, flash. ls lists the directory files. The WebSocket server file ws1pi is present. Typing man displays all available upysh commands. Head and cat displays the beginning and end of text files. I assume new file creates a new file. mv to move a file. rm to delete a file. mkdir to make a directory. rmdir to remove a directory. cp to copy a file. And clear can be used to clear the REPL screen. Import ws1 starts the WebSocket server. It's now running and waiting for client connections. Let's give it a test. Open a new terminal on the Pi. pip3 install WebSocket client installs a Python WebSocket client library. It provides WebSocket client connections from within Python programs. Open idle3 and in the Python shell, from WebSocket, import create connection. Create a connection called ws. For the URL, ws://mpi.local. This connects to the WebSocket server on the ESP32 and fires the accept callback, which in turn starts the hardware timer to poll the temperature sensor every 3 seconds. The ws recv method shows the received JSON data, which includes the time of the reading, the sensor temperature, approximately 26 degrees Celsius, and the internal ESP32 temperature of about 68 degrees Celsius. recv again, and notice the time is incremented by a few seconds. The sensor temperature is the same, but the internal has dropped about half a degree. WSSend sends the text hello world to the WebSocket server. Switching back to the REPL shows the text was received and printed to the screen. Of course, instead of a simple text message, commands or binary data could be sent to control the device, such as an LED, a relay, a display, a motor, etc. Now let's create a React app on the Pi to interact with the WebSocket server. React requires a newer version of Node.js than what currently comes with Raspbian. Node TAC-v indicates that the Pi is running version 4.8.2. Before installing the newer version of Node, the existing components should be removed. Sudo apt-get remove node-red, sudo apt-get remove Node.js, and Node.js legacy. Next, curl is used to download and run and install, which installs the Node.js version manager and updates Node.js and npm to the latest versions. Node.js version 9.10.1 is now installed. Before proceeding, a reboot of the Pi is required. Again, the Node version is now 9.10.1 and npm is at version 5.6.0. The next step is to use curl to install a dependency manager called Yarn, which facilitates creating React apps. Yarn TAC-v indicates that Yarn version 1.6.0 is installed. Okay, that's it for the tools. Now for some React code. cd into the Documents folder. The easiest way to get started is by using yarn create React app. The project is called ds18sock. Create React app generates a React application and does not require any build configuration. There's no need to mess around with Webpack or Babel. Everything gets pre-configured for you and you can just start writing code. That took 109 seconds, but the one command created a working React app that's ready to go. ls shows the React app folder ds18sock. cd into the folder and yarn start. This fires up the development web server and launches the browser with some sample code running. Any changes to the React code will cause the browser to automatically update. ReactJS is an amazing tool for building user interfaces. This video is not meant to be an in-depth tutorial on React. That would require several videos. Instead, I'm just going to walk through how quick and easy it is to build a UI. Control-C is used to stop the server. React is built with components, which let you split the UI into independent, reusable pieces. Creating a complex application can be a daunting task. Components let you focus on smaller pieces and thereby chip away at the larger goal. Many great open-source React components are available on a website called npmjs.com. Since we're using a temperature sensor, I'll search for a React thermometer and choose React thermometer component. This one looks good. A graphical thermometer with a numeric temperature label. It can be installed by using the yarn add command. This automatically adds the component to the project and resolves any dependencies. I'll also add React loading, which is a basic loading indicator, prop types for type checking, and MobX and MobX state tree. Error. Okay, I forgot the add command. Let's try again. That's better. MobX is an application state manager which can be used with React. I find it much more intuitive than Redux, and it doesn't require copious boilerplate. MobX state tree builds on MobX and provides a container that leverages the best features of immutability and mutability in a very opinionated approach. It lets you create a component model for your data. It's basically a library that helps you organize your application state. Don't worry if that sounds vague or meaningless. It's really not that complicated, but I think you do have to see code to understand, and all the code in this video will be available online. Okay, all the necessary component packages have been added. Here's the sample project generated by the Create React App Starter Kit. Most of the relevant sample code is in the src or source directory. Add a new folder called Models. This will hold models which are the core of MobX state tree. Models describe what the data looks like and performs type validation. Create a new file called sensors.js. This will describe the shape of the data for the DS18B20 temperature sensor. Import types from MobX state tree. A DS18B20 type is defined. Types consist of models, views, and actions. Types model holds the properties. This sensor has a temperature property to hold the current temperature in Celsius. 0 indicates it's numeric, and the default value is 0. Is ready indicates if the sensor has temperature data available. False indicates it's a Boolean, and it defaults to false. Actions perform operations on models which are otherwise read-only. A single action, set temperature, updates the temperature property. It also sets the isReady property to true to indicate sensor data is available. Views returns data derived from properties. MobX recommends storing as little state as possible in models. For example, instead of storing the temperature in both Celsius and Fahrenheit, only Celsius is stored, and a view called convertFahrenheit returns the conversion upon request. Export DS18B20 as default, and the sensor model is complete. Next, a model called Socket.js is added to handle the WebSocket client connections. Apply action is imported from MobX state tree. It's used to perform model actions. A default function called syncStoreWS is exported. It takes a socket and a sensor model. The onSocket message function takes a handler which is fired upon socket on message. For example, when the WebSocket server on the ESP32 transmits new temperature data. The handler is passed the parsed JSON data. If the data contains a field called temp, then apply action is used to fire the sensor's set temperature action with the received data. Next, a new folder is created to hold components. A new React component called temp gauge is added. This will display the thermometer component. React is imported. Prop types is imported for type checking. Import observer from MobX React. This is used to turn components into reactive components. When the underlying data changes, a reactive component will automatically re-render, and thanks to React, instead of the whole web page inefficiently reloading, only the parts that need to be updated are changed. Thermometer is imported from React Thermometer component. This is the thermometer component from the npm.js website that was added using Yarn. React Loading is imported from React Loading. This is the simple visual loading indicator that was also added using Yarn. Temp gauge is defined and is passed props. These are properties passed when you create a component. The props include a sensor, and if the sensor's isReady flag is true, then a div is returned containing the thermometer component, which has several properties. The value prop determines the thermometer temperature and is set to the sensor's convert Fahrenheit view. This converts the Celsius reading from the DS18b20 to Fahrenheit and displays it on the thermometer. The other properties are pretty straightforward. Min-max temperature range, the steps between ticks, degree format, and size and height. If the sensor's isReady flag is false, then the React loading component is displayed. It's set to spin in a blue color with dimensions of 100 by 100. Finally, prop types are added for type checking. This ensures the React component has passed the required properties in the correct type. This is a good practice and it helps in debugging. The temp gauge should receive a sensor comprised of the isReady boolean, which is required, and the convert Fahrenheit string, which is also required. Temp gauge is the default export, and the MobX observer is used to ensure this component is reactive. In other words, anytime the underlying temperature data changes, the component will automatically update itself. Okay, now the models and components are ready to be used. Open index.js, which is the app's starting point. Delete most of the sample code. The syncStoreWS function is imported from models socket. DS18b20 is imported from models sensors. A constant socket is defined as a new WebSocket client and passed to ESP32 WebSocket server's MDNS address. The sensor is created using the DS18b20 create method. syncStoreWS links the WebSocket and the sensor models. React DOM renders the app to the DOM and passes the sensor property. The app component is the final part of the program. Open app.js. Let's start from scratch. Erase all the existing sample code. React is imported, prop types is imported, the React logo SVG file is imported, the sample CSS style sheet is imported, and a temp gauge component is imported. App is defined and returns a div container. A header contains the React logo image. An H1 displays the web page title. Temp gauge is added. This is the temp gauge component with the thermometer display. It's passed the sensor prop. Prop types ensures that the app component receives the sensor prop. As before, its shape includes an isReady boolean and a convert Fahrenheit string. App is exported as default. Okay, in theory the React app should be ready to go. In the PyTerminal, ls shows the code, and I made a mistake. The components and model folders should not be in the root. Instead, they should be in the source folder. mv components models tact src moves the folders to their correct location. Verify with ls and lssrc. That looks correct. Yarn start serves up the React app. The development server starts, and a browser is open to the localhost port 3000. A loading indicator displays while the WebSocket connection is created. As soon as the WebSocket server sends a data packet, the thermometer is displayed, 74.97 degrees Fahrenheit, and the thermometer component will automatically refresh when new data is received. I'll warm up the sensor with my fingers. As the sensor heats up, the gauge updates in real time automatically. I hope you found this video helpful. You can support this channel by subscribing, leaving a like, and sharing. Thanks for watching.